Welcome to the tutorial on time division multiplexing (TDM). Time division multiplexing is a method of transmitting and receiving independent signals over a common signal path or channel by means of synchronized switches at each end of the transmission line, so that each signal appears on the line only a fraction of time in an alternating pattern. The time domain is divided into several time slots of fixed length, one for each subchannel. A sample data block of subchannel 1 is transmitted during time slot 1, subchannel 2 during time slot 2, etc. One TDM frame consists of one time slot per subchannel plus a synchronization channel and sometimes error correction channel before the synchronization. The circuit combines signals at the source end of a communication link is known as multiplexer. It accepts the input from each individual end user, breaks each signal into segments, and assigns the segments to the composite signal in rotating, repeating sequence. The composite signal from multiple sources will be transmitted. At the receiver end, the individual signals are separated out by means of a circuit called a demultiplexer and routed to the proper end users. A two-way communication circuit requires a multiplexer and demultiplexer at each end of the long-distance high-bandwidth cable. This is the circuit used for time division multiplexing in the laboratory. Here, two signals, sine and ramp signals, are multiplexed. 20 kHz 7 volt square wave clock is used for time division multiplexing. That is, it assigns different time slots so that sine and ramp signals are multiplexed. For example, for positive half cycle of the clock, ramp signal is transmitted to the output. For negative half cycle of the clock, sine wave is transmitted. So in this way, the segments of sine wave and ramp wave are transmitted in a multiplexed manner. Now we will study the working of time division multiplexing circuit. Let me use the pointer. So for the positive half cycle of the square wave clock, so what happens in this case? We have two transistors, NPN transistor and PNP transistor, and collector of NPN transistor is connected via resistor R5 to a 3 volt 200 Hz sine wave signal. There is one more transistor, SK100, which is PNP transistor, and collector of this is connected to a ramp signal via resistor R2. Now for the positive half cycle of the clock signal, the transistor NPN will be on. It will operate in the saturation region, and the transistor PNP will be off. It will operate in the cutoff region. So since the transistor SL100 being NPN transistor is in the on position, the sine signal which is connected to the collector of this transistor will be pulled down to ground. So we can see this red path over here. So sine signal will flow to ground, or it will be pulled down to ground since this NPN will act as a short circuit. Whereas the PNP transistor SK100 will be off. It will act as a open circuit, so there is no connection over here. So what happens is this ramp signal will flow via these two resistors R2 and R3 to the inverting terminal, and we will get the output. So for the positive half cycle of the square, we will get a ramp signal at the output for the duration of that of the positive cycle. So we can see this green colored line which indicates the components which will be present in the equivalent circuit. This is the equivalent circuit for positive half cycle of the clock signal. As we know, we are applying a 7-volt clock signal. I'll take a moment to use a marker. So we have here the positive half cycle of the clock. Peak to peak of the clock signal was 7 volts. So when we consider only the positive half cycle of the clock, it will be plus 3.5 volts. Now for this particular case, as we know, NPN will be on and PNP will be off. So this will be in the cutoff region. And V1, that is the sinusoidal signal, will be pulled down to ground. So this is the equivalent circuit for the case of positive half cycle of the clock. So we will have non-inverting terminal of the op-amp is connected to V1, which is equal to 0 volts, and V2, which is equal to 2 volts ramp signal. So now this circuit, if we can see, this works as a non-inverting summer. So how to analyze the output of this particular circuit? So what happens here is we have to consider the output of this part of the circuit by considering one input at a time. That is, the output of the summer is analyzed by using principle of superposition theorem. So the superposition theorem, according to superposition theorem, the voltage at pin number 3 is obtained by considering one input at a time and assuming the other input as 0, and then adding those two signals will give us the voltage at this particular terminal. For the first case, by considering V2 as 0, the voltage at pin number 3 will be, by using voltage divider rule, 0 volts into 1 plus 1, these two resistors are in series, so 0 volts into 2 kilo ohm divided by 1 kilo ohm plus 2 kilo ohm. That will be the voltage here. Then for the second case, by assuming V1 as 0 and V2 as 2 volts, so voltage at pin number 3, that is at the non-inverting terminal of the op-amp, will be 2 volts into the output resistance is 1K divided by 1 plus 1, 2K plus 1K. So both the times we are applying voltage divider rule by considering only one input and other as 0. So initially we considered V1 only and V2 as 0 and applied voltage divider rule at this point. For the second time we have taken V2 as 0 and considered only V1 and applied voltage divider rule to obtain the voltage at non-inverting terminal, and these two are added to get the voltage at pin number 3. And then we can, to find the output voltage V0, we can use the formula of non-inverting amplifier. So that is V0 is equal to the gain into Vin. So to find the gain, we have the formula as 1 plus RF by R1. So RF for us is a feedback resistance here, which is R6, and the input resistance will be R7. So gain will be 1 plus R6 by R7 into Vi, For the negative half cycle of the square wave clock. Now what happens for the negative half cycle of the square wave clock? So here the NPN transistor will be off because of p-type base, and PNP transistor will be turned on because of the n-type base. So this will be off, or our SL100 will operate in cutoff region, and SK100 PNP transistor will operate in the saturation region. Now since this is on, this will act as a short circuit, and this RAM signal will be pulled down to ground. So we can see a red line over here which shows the path. Okay. Then since the NPN transistor SL100 is off, it acts as an open circuit, so there is no connection over here. So the sine signal 3 volts peak to peak 200 Hertz will flow to the output through this terminal 3, or this will be given to the sine signal will be given to the non-inverting terminal of the op-amp. The equivalent circuit will have the sine signal R5 1 kilohertz, R4 1 kilohertz, and R3 1 kilohertz, and the other terminal of R3 is at ground potential because this part of the circuit will be pulled down to ground. So we can see the equivalent circuit in the next PPT, in the next slide. So here these are the components which will be present in the equivalent circuit. A sine signal R5 1 kilohertz, R4 1 kilohertz, and R3 1 kilohertz. The other terminal of R3 is grounded, or it is at the ground potential, and this is again so equivalent circuit for negative half cycle of the keying signal. So for the negative half cycle of the keying or the clock signal, the voltage is minus 3.5 volts. So we have two resistances of 1k in series, and this terminal is connected to a sinusoidal signal of 3 volts, and we have one more resistance of 1k. The other terminal is at ground potential, and this junction is connected to pin number 3, and the terminal 2 or inverting terminal is connected to a junction between R6 and R7. R6 acts as a feedback resistance, R7 acts as a input resistance. So again we can analyze the output by using the non-inverting summing amplifier concept. So what happens here now? Again, to analyze the voltage at pin number 3. What is the voltage at pin number 3? We have to apply the principle of superposition. That is, we have to consider the output voltage at pin number 3 by considering only one source at a time. So initially, if we consider only V1 and assume the other source, whatever it is, we have to assume it as 0. So in that case, the voltage at this point will be, by using voltage divider rule, V1 into 1k divided by 1 plus 1 2k plus 1k. And for the second case, by considering this voltage as 0 and considering the second voltage source, so 0 volt into the output resistance will be 2 kilo ohm divided by 1k plus 2k. So again, voltage divider rule, and adding these two output voltages obtained by considering one source at a time and assuming other one as 0 each time, we get the potential at non-inverting terminal. So then we can obtain the output voltage by using the formula of output voltage of a non-inverting amplifier. So again, V0 is equal to gain into Vin. Vin will be the voltage at the non-inverting terminal. So R6 is the feedback resistance, R7 will act as the input resistance. So the V output voltage expression will be V0 is equal to 1 plus R6 by R7 into the voltage at pin number 3. This is the circuit used for demultiplexing. Demultiplexing is recovery of two band limited signals which are multiplexed. So TDM input, the time division multiplexed input, is the input to the demultiplexing circuit. So here we have two transistors, SL100 which is an NPN transistor and SK100 which is a PNP transistor, and two low pass filters. So in the upper channel we have to get back one of the signal, that is sine. At the lower channel we have to get back M2 of t, the ramp signal. So we have two message signals, sine and triangular signals, which are multiplexed. Now in the demultiplexing we have to get back those. So we have time division multiplexed signal as the input, and the output will be the individual band limited signals. So here there is one more input to the demultiplexing circuit, that is the same clock signal of 7 volts 20 kilohertz square wave. We can see the analysis. So TDM input is given over here, which goes to the collector of this NPN and PNP transistors through the resistances R2 and R3. And we have a clock signal, the same clock signal which is used for multiplexing is used here for demultiplexing, a 7 volt 20 kilohertz signal which is fed to the base of NPN and PNP transistors. Now what happens to the positive half cycle of the clock? When positive half cycle of the clock is given to the base of NPN and PNP, NPN transistor will be turned on, it operates in the saturation region, and PNP will be turned off, it operates in the cutoff region. So here there will be an open circuit, here there will be a short circuit. Due to short circuit at this point, the TDM signal which is available at the collector will be flown down to ground, and the TDM signal which is available at the collector of PNP transistor will flow to the low pass filter, and the low pass filter is designed to get back the triangular wave. So what happens here is, for all the positive half cycles of the clock we get the segments of triangular signal at this point, and then a low pass filter which is designed for 400 Hz, which is the frequency of the triangular wave which is used for multiplexing, we get a smooth triangular wave recovered at this point. So we have a formula for low pass filter. F is equal to 1 by 2 pi RC. F is taken as 400 Hz, the frequency of triangular wave. C is assumed as 0.1 microfarad, and R is found, and R is equal to 3.9 kilo ohm. So M2 of t is a triangular wave which is recovered at this point. Now for the negative half cycle of the clock, NPN transistor will be off, it acts as an open circuit, and PNP transistor will be on, it acts as a short circuit. So the TDM signal will be flown down to ground, so there will not be any signal over here. And since this is open circuit, there is no connection, so TDM signal will not flow to ground, it will go to the low pass filter. Now low pass filter here also is designed for the same frequency, 400 Hz. That is because for all the negative half cycles of the clock we get back the segments of the sinusoidal signal which is multiplexed during the multiplexing, and this low pass filter is used to smooth out the signal, to remove the components of clock present in it and get back the smooth recovered sine wave. Now why this filter is also designed to the same R and C value, even though the sine wave frequency is 200 Hz, or the recovered sine wave frequency should have a 200 Hz, because the same signal is used for multiplexing. Since the sine wave signal here is 200 Hz and this frequency is less than the frequency of the triangular wave which is 400 Hz, the low pass filter which is designed for 400 Hz should satisfy the frequency of 200 Hz. That means the low pass filter which can pass the frequencies below 400 Hz can also pass all the frequencies below 200 Hz. That is because 200 Hz is less than 400 Hz. So we can use the same RNC values. So this is about the demodulation or demultiplexing. The upper channel is used to recover the sinusoidal signal, and the lower channel is used to recover the triangular wave signal. The low pass filters are designed to pass all the frequencies below 400 Hz. So this RNC values will satisfy for both of these cases, the recovery of sine wave as well as recovery of triangular wave. We can also design these RNC values for exact 200 also. So we can take f as 200, assume C and find R, and that value can also be used here. So we have to remember that the for all the negative half cycles we get back the sinusoidal signal at this point, and then a low pass filter to smooth out the signal. For all the positive half cycles of the clock we get the signal over here, the segments of RAM. So these are the waveforms. The data 1 sinusoidal signal of 200 Hz, data 2 a RAM signal of 400 Hz, and a 20 kHz 7 volt clock signal, and the time division multiplexed output. These two signals are multiplexed for time slots of these positive and negative clock cycles. For positive half cycle we get the sine at the output, negative half cycle we get ramp. Again for the positive half cycle we get sine, and for the negative half cycle we get ramp. So all the positive half cycles the sine signal is obtained at the output, the inverted, and for all the negative half cycles we get components of ramp. So in this way the two signals are multiplexed. So clock signal is mainly used to give the time slot. So and we have a recovered signal data 1, which is a sine signal which is recovered at the upper channel, and recovered data 2 which is recovered at the lower channel of the demultiplexing. Thank you.